I want you to recognize on this EM spectrum as we go from gamma rays, that's the Greek letter gamma, all the way up to radio waves, that light comes in a very long spectrum. There's a big region of space, or a big region of wavelength or frequency that light covers, the electromagnetic spectrum. And the visible light covers only a very small part of that. And it is by color. I'll give you the Roy G. Biv here in just a second, but on this end, I have blue light, and on this end, I have red light. And it goes, I would have orange and then yellow and then green and then blue. So it's going to increase in order of energy. So blue light, for example, has higher energy. Red light has lower energy. Red light also, by the way, has a long wavelength and a or low frequency. And then blue light has a short wavelength, or small wavelength, and a big frequency, or high frequency. Okay, so you also need to know about visible light and how it fits within the larger electromagnetic spectrum. Visible light is in, you probably know this mnemonic, Roy G. Biv. Or really, the I is not really part of the spectrum, so we'll just do Roy G. Biv. This goes from an energy of approximately 1.8 electron volts all the way up to 3.1 electron volts. Let's throw back to the previous chapter here for just a second, because what I've done is given you a new unit for energy, the electron volt. Remember, volt is a unit of potential, and it is a measure of energy per charge. E is the fundamental unit of charge, and so it is just a charge. So when I multiply E times V, then that gives me a unit of energy. So what I have here is a new unit of energy called the electron volt. You may have heard that term. No, you probably haven't. But the electron volt is a fairly common unit of energy, especially when we're talking about atomic physics. I think we'll get back to this when we do nuclear physics later in the semester. It has to do with how much energy takes in the atom to go from one electron orbital to the next. So this is a very simple model of the atom. There's our nucleus in the middle, and I have these electrons can move in between energy levels. And say in this particular atom and these particular energy levels, I'm separated by about 1 point eV. I think this is the hydrogen atom, I'm not sure. But anyway, in a particular, all the atoms are different and the orbitals are different to the energy between them. But let's say, for example, that there is a difference in the energy level of 1.8 electron volts. That means that when an electron goes from this energy level down to the lower energy level, or excuse me, to the upper energy level, then it takes energy. So what's required is that you have a photon that comes into that electron, excites it, and moves it up to a higher energy level. On the other hand, what if I have an electron at a higher energy level and it moves down to a lower energy level? What happens there is it actually emits a photon. So it actually produces light. So here I'm absorbing light, and here I'm emitting light. And the light's going to be of the same energy of 1.8 electron volts, and that would be, the 1.8 electron volt would be on the red end of the spectrum, so it would be a red photon. It would appear to you to be red. So visible light is caused by electrons moving in or out of energy states. The energy range for visible light is from 1.8 to 3.1 electron volts. And that's the range of energy required to move or remove electrons from many molecules and atoms. So to you have to put in this amount of energy to move an electron from one energy level to another, or you put in that amount of energy just to remove it completely. Now, there are higher energy processes that can move electrons between different energy levels for other atoms as well, but as far as our visible spectrum, it's from 1.8 to 3.1 electron volts. Know what the EV is, know what an electron volt is, it's a measure of energy. Know that electrons moving back and forth between these energy states will actually cause you to emit or absorb a photon or light. I think that's it. Okay.